morning, everyone. Thank you for attending the fifth day of the International Virtual Class on Introduction to Volcano Monitoring System. Um, today, there will be two sessions for this day, and the first session will be delivered by Dr. Asep Saepuloh. He will give a lecture about InSAR monitoring. And then for the second session, there will be three speakers. And without further ado, for the first session, I would like to welcome Pak Asep Saepuloh. Pak Asep Saepuloh, the time is yours. Thank you.
Thank you, Ms. Dian and Pak Zul. Good morning, everyone. So this is maybe for today is the first speaker. So maybe we'll have about 1 hour to discuss about volcano monitoring using InSAR. Okay, I will make this slide so. Could you see my slide, Ms. Dian?
Yes, sir.
Okay, thank you. Okay, good morning, everyone. So my name is Asep Saepuloh. I'm from Department of Geological Engineering, Faculty of Earth Sciences and Technology, Bandung Institute of Technology. So today we will discuss about InSAR monitoring with the study case of Agung Volcano. So in this course, so if you have question, so directly you might open your mic and speak loudly, or if you difficult to do that, so please write down your question or anything about the course using chat box in this Zoom facility. Okay. And this outline of this morning course, so we will discuss about five things. The first one about the principle of InSAR. The second one about volcano deformations. The third one about Mount Agung on the field. And the last one about Mount Agung monitoring. So in this lecture, probably similar with the previous one, that we try to use any tools or equipment to observe the volcanic activity. So in this method, we use a remote sensing technology. So that's why in the first sections, I will explain a little bit about remote sensing technology. Because without basic knowledge about this technology, so it's difficult to understand about the InSAR. InSAR kind of the relatively new technology applied to the volcano. Usually this technology used by our colleagues from geodetic to measure millimeter scale of the land subsidence. So this is a very good technology when we apply this one to volcano in certain condition actually, because not all conditions we will have the good information obtained by InSAR. So that's why in the beginning, so we will discuss about the remote technology using the radar, because InSAR dealing with the radar technology. If you're familiar with this kind of technology, so we will discuss together. Probably you might add some explanation more deep about this technology. So I'm afraid if you not all of you familiar with radar technology. So that's why I will discuss a little bit about this technology at the beginning. Okay. The left figure is kind of the InSAR result. So this is deformations. Also, this is in the volcano. So, so this is only example when we do the technology observing the ground movement, especially in the old volcanic. So in the ending of this course, we will discuss about the young volcano. But this is kind of the another case when we deal with the old volcano. So the left part is the geothermal field in an old volcano in West Java. So we can see the red pixel and green pixels and any pixel in the image indicating the digital value of the deformations. So of course, it will be difficult if we measure each point at the ground using the direct measurement. So we will need times, we will need equipment, and of course, we will need cost. But using this kind of method, we can do quickly and cheaply, relatively cheaply, as long as we understand how to deal with the data and how to read the data. As you see here, so we can see the deformations velocity indicating by the color. There is some part is uplift and some part is subside. So uplift is, I read here is turun, subside naik in this figure. So, okay. So we will discuss about this one, how we can apply this technology in the volcano. Okay, let's continue. Okay, in the first thing, so I would like to talk about the early success of the InSAR technology, as I know, of course. So maybe you know better than me. So this is kind of the good story when the InSAR rise to the surface. So I saw you here in the left figure. Okay, this one. So this is kind of the beginning of the InSAR. It seems like that the InSAR or remote technology using the InSAR method could image of an earthquake. Usually, we capture the image of the earthquake only the destruction or destroying area, and we capture with the picture using camera or satellite camera sensors, something like that. Only these destructions or destroyed building or urban area or something like that. But using InSAR, we could see the image of the earthquake. So you see here, so there is kind of the, we call this is fringes. This kind of the color, is kind of the fringes, we call fringes of interferogram produced by the InSAR technology. So this is this InSAR imaging the Landers earthquake on June 28 in 1992. So this is the largest earthquake hit Southern California in 40 years. So the moment magnitude is about 7.3. Luckily, this area is inhabited, so no fatalities occur here. But we could see here, this is kind of the propagation wave of the earthquake, showing by the interferogram. Okay. This is the early, I think, so people understand, oh, so the remote technology can image the earthquake. And the left part, I'm sorry, the right part, so it's similar case. So we could see here, we call this is butterfly fringes. So butterfly fringes is the successful method or successful processing of the InSAR. We see kind of the butterfly like this. So this is also the interferogram. This interferogram produced by InSAR. So this is the bomb earthquake in Iran. So the magnitude is lower than the Landers earthquake. So it's about 6.6. But the earthquake occurs at the dense area. So the total death amount 26,271 people get lost at this moment, at that time. So inside we can see the propagation of wave indicating the interferogram. It's not just propagations, but we could get the value of the deformations. Which area uplift very much, which area subside very much. And from here, we could predict where is the fault. Fault is the source of the earthquake, you know, right? So that's why we can see the propagation of the wave controlled by the fault line. Okay, this is the first case that the InSAR applied to the earthquake. But now we will shift this technology to the volcano. Of course, different characteristic from the earthquake and volcano, we will see the different fringes behavior. So probably it will in volcano usually it's difficult to get the butterfly like this. So the butterfly is good success for the InSAR processing, but for the volcano it's not like this. Okay, so we will see how this InSAR can work for volcano. I continue. If you have a question, please raise your hand. Okay, clear. I close my note. Let's continue. And then slightly I will talk about the remote sensors. Remote technology, how can deal with this kind of the good information. Remote technology or remote sensing. So we have two kinds of sensor utilized on board the satellite. The first one is optical sensor. The second one is non-optical sensor. What are they? Optical sensor works on visible to thermal infrared region. This is the optic. As you know, as our handphone, we have the camera. So it's optic. Why optic? Because they use the lens. Another technology, another sensor use microwave. We call this is radar. So this is non-optic. They don't use any lens because the wavelength is not covered by the lens. They use antenna. So we are dealing this technology, this remote technology using the InSAR utilized by the radar sensor. Okay, so we use the non-optic. So another technology using non-optic sensor is the first is radar, and the second one is LiDAR, and the third one is sonar. I'm sorry, the LiDAR is still optic, of course, because it's use light. I mean, this is the active sensor. Usually use the radar. So radar, we will dealing with this today. Radar is radio detection and ranging. So in this technology, we could detect object and we could measure the range or the distance. So using technology, this radar, so we could measure the distance of the object from the sensor, and also we could recognize the object. What are they? Okay. So, for example, we want to detect the ship on the sea. So we could use this technology. We could use radar to detect the ship. Besides this, we could measure the range, the distance from the sensor to the ship. So that's why when we use the temporal observation, we could measure the speed of the ship. If the ship is moved another point to others, so we could measure the speed, you know. So that's why this technology is used. So that's why this technology can measure the deformation, because this technology could measure the range. Repeating time the observation, we could get the velocity, the change of the object at the surface. Okay. Another one is similar with this is LiDAR, but LiDAR using light, so they are using optic, and also sonar. Sonar using sound, and not any radio anymore, so it's using a sound. So this technology using the active technology, as we will discuss using the radar. And this is the important one. So today we use InSAR. Why InSAR? Why InSAR can measure the deformation? Because as I said before, the the radar can measure the range. The range of the object using radar pulse from the sensor. So they give the pulse like this, the red line. Okay. This is the pulse. And then the pulse will be interact with the object on the ground. For example, hose and trees, and the object will interact with the electromagnetic wave from the radar, and then will give back the signal. We call this is backscatter. So the return signal from the object. The signal will reach the receiver from the sensor. Okay. The sensor will record the time. Okay. The time travel of the signal from the source to the object and the object to the source twice, and then they will record, and then they will convert to the distance, because they know the velocity of the speed of the signal, so we could get the distance simply like that. And then, okay, this illustration, the signal come from the trees and from the hose, and then we will get the signal like this. So the x-axis is time, the y-axis is pulse strength, the power returned to the receiver. Okay, the power returned from the hose will be different from the power returned from the trees. Okay, this different power is the basis for the recognition of the object. Beside that, so we have the time return from the hose, the time return from the trees. So we can make this calculation to get the distance. Repeat time of the measurement of the distance, we will get the deformation. Okay, so we will discuss about deformation starting from this, starting from the signal return from the object. Okay. Okay, I will continue. If you have a question, please raise your hand or speak up. This is another good explanation how InSAR works. I obtained this cartoon from the internet. So this illustration is easy to understand how the InSAR can measure, and because we will have the certain conditions when we do with InSAR method to get the deformation. Not on all places can get good measurement of deformations. So we have to understand the difference about this. Okay, I show you here the surface. As we know, at the surface we will have many objects: home, trees, bare land, water, building, pavement, and others. This is the ground. Firstly, the sensor will observe the surface. Okay, we call this is first acquisition. This is the first time the sensor, the radar sensor, observe the surface. The first observation we call master. In InSAR, we call this is master. At the first acquisition, we have the distance, we have the range from the sensor to the surface, for example, to the ground, to the host. We call row 1. Okay, this is range from the first observation. And then, secondly, there is something happen, geological change at the ground. That's why some place subside or some place uplift. So subsidence and uplifting is the object of the measurement of the InSAR. And then the second acquisition occurs. The second time of the observation done by the satellite. And then we get the second range. We call row 2. Row 2 is the distance, the second distance from the satellite to ground. And then we compare row 1 and row 2, okay, to get the deformations. Okay? So we call this is change in line of sight, the change on the satellite view. Okay. The process is not simple actually inside of the program. So we have to consider this is not only direct measurement of the distance like this actually inside, okay, inside the program. So they calculate the phase because this is a wavelength, the wave propagation. So what the program can do is measure the phase. So the different phase, shifting of the phase from the master image and the second, which we call slave image, the shifting of the phase is the basis of the calculation of the deformations. So the delta rho is the shifting of the phase from two acquisitions. So the different phase attributed to the deformations. Okay, I continue. But the problem is usually occurs in tropical area as Indonesia. So we located in the tropical area. It's not easy to get kind of the deformations using the phase. Because why? Because we have the atmosphere. Our atmosphere fully by constituent such as aerosol, water vapor, gases, and others. These constituents contribute to the to the wave propagations. So the wave will cause delay here, delaying the propagations. So it will make fake deformations, not the true deformations. So this is the hard thing when we deal with this kind of method applied in the tropical area. It's really difficult, but it's not many way actually, but it's basically it's difficult if we compare to the not tropical area, for example, torrid area, or I'm sorry, for example, subarid area or arid area. In tropical area, it's difficult because our atmospheric conditions. This is the basic. So the one method we can deal with this kind of the difficulty of the atmospheric conditions, we use persistent scatterer. So this is kind of the relatively new method. We said another latest method. So usually we use the persistent scatterer. What is persistent scatterer? Persistent scatterer means the consistent point at the ground that the radar can measure the range. So this consistent point we call persistent scatter will be a good signal to get the deformations. For example, if we have some area like this, so the good point we call this is persistent, and another points we call distributed scatter. Persistent scatter usually is a fixed infrastructure or fixed made. For example, the tower of the electrical like this, or sometimes the building. So it's sometimes make a good scatter, or sometimes pavement. This is will be a good scatterer. Another points, for example, bare land, vegetation area, and others, it will be a distributed scatterer. So using this method, we use only the persistent scatter over long period of observations is the key. So using the lot of data, statistically, we can predict where is the signal from the ground, where is the signal from the atmosphere. So we could exclude the signal from the atmosphere because we want the signal from the ground. Okay. Okay, I continue. So this is the basic idea of the InSAR and also the persistent scatterer that I will show you the result at the Agung volcano. Okay, break a moment, 3 minutes. So if you have a question or anything about this course, please speak up or write down in the chat box.
Excuse me, Asep Saepuloh, in the chat box there is a question from Harmita Lestari.
Okay, thank you, Badia.
Okay. The question is the dimension of the house or tree or something like that can influence the signal that receives to the sensor?
I see this question. Dimension of the house of tree or something like that. Can you okay, good. This is good question. Thank you, Miss Harmita. Yes, when we talk about the deformations using InSAR, the scale is millimeter. Millimeter deformation. For example, if our ground is moved to the low or to the up is 1 centimeter, we can detect successfully. But the problem is the image, the radar image is limited by the spatial resolutions. The spatial resolutions will control the deformations. For example, our image use the resolution 10 meter. Spatial resolution 10 meter, it means if the dimension of the host is larger than 10 meter, the deformation of the host in millimeter scale we could detect. Okay, but if our image resolution is 20 meter, of course, the host with the dimension less than 20 meter could not be detected easily using this kind of InSAR. Even though the deformation of the host is large, okay, but we are limited by the spatial resolution. Okay, but if you talk about the signal, of course, the signal can reach the host, even though the resolution is, even though the dimension of the resolution is lower than the spatial resolution of the image. But it will be combined with another scatter, another object in the radius of resolution. For example, in the 10 meter resolution, in 10 meter, only not host, but also there is a vegetation, also there is a bare land. So the signal is combined from the all object in this radius of the resolution. Okay. Okay, I hope this make clear.
Thank you, Pasep. There is another question from Marco Delgado. The question is, what is the best spatial resolution for InSAR?
Okay, this is also a good question. Thank you, Mr. Marco. So uh, the best spatial resolution is depend on our purposes. Okay, if our purposes is large, for example, the volcano. So we talk about the body of the volcano, the large. Okay, the body of volcano is sometimes kilometer scale. So the resolution 30 meter is good. 30 meter or 20 meter is good for kind of the volcano deformations. But if our target is smaller, for example, the city, the deformation of the bridge, for example, so the highest resolution is necessary. For example, 5-meter resolutions or 3-meter resolution is necessary if our object is small. How we can get this kind of resolutions? At the first, of course, depend on the sensor itself. The sensor capability is possible to obtain the high resolution or the medium resolutions. Okay, so the base resolution is depend on the target. Okay, Mr. Marco, is it clear? I hope this is clear. If not, so please ask again. Okay. Next question, Badia.
Yes, there is another question from Aldo. How often does the radar emit pulses each second or another time?
Good question. Sir, the pulse is sent by the transmitter is very fast. I'm sorry, I'm the forget the number, but in second there's many pulse. So it's the repeat pulse is very much is depend on the sensor. So because the repeat time of the pulse will contribute or will influence to the resolution. So each sensor have a characteristic of the emitting time of the pulse each second. For example, 6 times per second or 80 times per second or 100 per second it's depend on the sensor. So the pulse is very rapid every second.
Okay, thank you, Asep. There's another comment from Marco Delgado. He asked, and can we use a better resolution for volcano like 10 meter or less?
Okay. Okay, this is also a good point, Mr. Marco. So of course we could use the 10 meter, but please be careful when we observe the volcano in high resolution, for example 5 meter or 3 meters. We have to consider the deformation from another thing. For example, from the landslide, from the shaking of the volcano, and that's the sector is moving or sliding, gitu ya. But this is not related with the magmatic system beneath the volcano. Or if we use the high resolution, for example 3 or 5 meters, be careful about the another source of the deformations. Okay, for example, another thing, human activity. If there is not around the area, for example, there is a kind of the mining area. So the area sometimes not stable and then getting down. So we could measure this kind of subsiding landslide using the high resolutions, but please be addressed. This is not related with the volcano. So this is maybe related with the human activity. So this is the limit time when we use the high resolution of the observations. Okay, thank you.
Okay. Thank you, Pak Asep Saepuloh. Um, is there any question from the participant? If there's no more question, shall we continue, Pak Asep?
Okay, let's continue.
Thank you.